Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 8, 2026, just yesterday. It introduces a technique called Learnable Multipliers that decouples weight scaling from optimization artifacts, boosting downstream benchmark performance by over 1% for both Atom and Muon optimizers. The paper is titled Learnable Multipliers, Freeing the Scale of Language Model Matrix Layers. And as we'll see later, the implications for model training are quite significant since this method offers performance gains with no added latency during deployment. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 demonstrates how learnable multipliers allow the model to escape suboptimal scaling artifacts. In the top left graph, the green curve shows the standard frozen projector norm, which suffers from a sharp U shape, indicating high sensitivity to the initialization scale. Conversely, the blue and orange lines for the vector and scalar projector norms are nearly flat, showing that the method robustly finds good solutions regardless of the forced scale. The top right panel explains this mechanism. While the matrix norms, shown in solid lines, are forced to vary, the learnable multipliers, in dashed lines, automatically adjust in the opposite direction to compensate. Moving to the bottom right, we see this pattern holds for MLP layers too, where adding learnable scalars flattens the loss curve compared to the sensitive baselines. So, Figure 3 illustrates how learnable multipliers unlock feature diversity across the model's width. The charts track row norms for the attention, multi-layer perceptron, and state space model projections. In the standard parameterization, shown by the orange spikes, the norms are tightly constrained to a single scale. In contrast, the blue histograms for the vector multipliers show a much wider spread. This variance indicates the model is successfully learning to emphasize important features and suppress others, creating a richer internal representation. While Figure 3 focused on width, Figure 2 shifts the analysis to depth-wise scaling. The leftmost chart tracks the ratio of block output norms with learnable multipliers against the baseline. You can see a clear upward trend where the ratio climbs well above 1, indicating that the model learns to significantly amplify the contribution of later layers to the residual stream. The middle and right panels explain how this happens by plotting the learned multipliers themselves. In the center, the output scalars generally increase with depth, while on the right, internal parameters like the SSMDT projection, shown in green, fluctuate sharply, suggesting the model specializes different layers for varying temporal scales. Table 1 compares scaling recipes for maintaining stability as model width, D, grows. The top row shows the standard approach where we only scale the learning rate. As the red values on the right indicate, this fails because the output norm grows with the square root of width, leading to instability. The second row fixes this by scaling weight decay with width, which keeps the output constant. Finally, the third row demonstrates that scaling the multiplier itself achieves the same stability, offering a robust alternative for large models. Alright, moving from stability to performance, Figure 7 presents a crucial ablation study on tuning complexity. The bar chart on the left compares final loss across 4 configurations, ranging from no tuning in red to full hyperparameter tuning in blue. Notice that for both Atom and Muon optimizers, the groups with learnable multipliers, labeled plus LRM, consistently achieve lower loss than their standard counterparts. What is especially interesting is the green bars within the LRM groups. They show that simply tuning the learning rate is enough to match the performance of the fully tuned blue bars. This implies that learnable multipliers automate the tedious work of tuning forward and weight decay parameters. Finally, the graph on the right tracks the loss difference over time. Since the values stay negative throughout training, it confirms that adding these multipliers yields a consistent improvement in learning efficiency. So, Table 2 shows how these training improvements translate to downstream tasks after a longer 200 gigatoken run. In the average column on the far right, the Atom optimizer improves from 30.8% to 32% with learnable multipliers, a clear gain of 1.2%. The stronger Muon optimizer in the bottom rows sees a similar 1.1% boost. Interestingly, the gains are concentrated. Reasoning tasks like BBH and Math Level 5 see significant jumps compared to knowledge benchmarks, with BBH improving by over 3 points in the Muon setup. Wrapping up, 2 takeaways stand out. First, decoupling weight scaling from optimization artifacts allows models to find better solutions than standard weight decay permits. Second, since these multipliers merge into the weights layer, it is effectively a free performance upgrade for production models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.